It's my great pleasure today to introduce our speakers, and the paper for discussion and for publication in Series B is entitled Assumptionlean Inference for Generalized Linear Model Parameters by Stijn, Vansteelandt, I'm not sure if I got that pronunciation correct, and Oliver Dukes from Ghent University, Belgium. Okay, Stijn, over to you.
Thank you very much. I would like to say that Oliver and I feel really honored, humbled, and really grateful with the opportunity to present this work for the Royal Statistical Society. There's two people I would like to thank in particular. Jamie Robbins, who's been a lifelong inspiration also for the presentation and work today, and also Mark van der Laan, with whom we were teaching a masterclass about a year ago, who made us realize more than ever that there's issues with standard statistical modeling, and this inspired us to think about how we could do better in the context of generalized linear models. I would like to apologize for people who attended the demo session. There's going to be slight bits of overlap, but in this meeting, we would like to concentrate a bit more on the philosophy behind the framework and why we made certain choices. And hopefully that can fit nicely into the discussion. So let me start with a brief introduction. Statistical models clearly are very dominant in data analysis for many reasons. They help us obviously to summarize the information in the data, to summarize associations between measurements. They also help us to address the curse of dimensionality. Like when we need to control for confounding, then ideally we would like to do the analysis. We would like to look at associations between exposures and outcome within strata of the population, but because of the sparsity in those strata, we would like to borrow information between strata, and models are really very helpful for that. Models are also used to help identify effects of interest, and that's very much the case in instrumental variable analysis. Models are clearly very successful, but they've also been very much a subject of critique, especially in recent years. I'm going to mention a couple of critiques fairly briefly. First, models can sort of lead one to report rather difficult to interpret parameters. This is very much the case, for instance, when analyzing or modeling a dichotomous outcome. We are very often drawn to using logistic regression, and then the usual parameters that we would report are odds ratios, which can be somewhat subtle to interpret. There is what Breiman called Occam's dilemma. That is, when modeling data, we may be a bit torn between going for a simple model that we can easily communicate to a broad audience versus a model that's hopefully correct, but likely more complicated. And these are very different aims. They are conflicting aims that may be really difficult to reconcile. Those compromises may induce model misspecification, and that may lead to bias in effect estimates as well as their standard errors. Excessive reliance on models, as I think is really common in practice, may also lead one to overstate precision. This is, for instance, the case in the context of generalized estimating equations, as explained in these papers by Mark van der Laan, where we usually ignore estimation of variance components, because if the model for the mean is correctly specified, then the asymptotic inference gives justification for that. But the more likely truth is that the model for the mean is misspecified, and in that case, we usually end up with excess variability not acknowledged by the usual sandwich standard errors. Also, when models are misspecified, it may often be rather unclear what we end up estimating, where a maximum likelihood estimator, for instance, is converging to, and whether what we end up estimating still makes sense and is somehow capturing the association of interest. Finally, model building algorithms, which we would commonly use in practice, hoping to prevent misspecification, they come with their own problems, because the standard inference that we employ in practice has been developed for cases where the model was pre-specified. And when we employ model building algorithms, that will usually give rise to excess variability because of the fact that under repeated sampling, we may not always choose the same model. So should we stop modeling altogether? Well, we can certainly do better by not using models to summarize the information in the data, and we can do that by focusing on pre-specified non-parametric estimands instead. And that's very much the focus of current developments, for instance, in causal inference. One estimand that has received a lot of attention is the mean of Y1 being a counterfactual outcome that indicates what the outcome would be for a given subject if that subject were treated. Under typical causal assumptions, we can identify this by first taking the expected outcome Y in the treated population. I will label those with A equal 1, and then we condition on confounders that or covariates sufficient to control for confounding of the association between A and Y. So first we predict basically what the outcome would be, and then we average those predictions across all people. This is a clearly defined estimand, and we can develop nonparametric inference for that based on the efficient influence function, which Oliver will say more about later in the talk. It turns out this framework basically accommodates all the previous concerns. I'm not going to go through all the reasons for that, but let me just give you one reason. So this non-parametric approach is still employing statistical modeling, obviously, to handle the cursor dimensionality, for instance, to learn how the covariates L relate to the outcome and how they relate to the exposure. But it's not using statistical modeling to summarize. And that implies, for instance, that no trade-offs need to be made between simplicity versus correctness. It also means that the modeling can go to a full extent. We can use flexible data adaptive strategies, even machine learning, hoping that we can prevent bias, that we can come up with the correct models here. And this is not complicating the end results, which is or can be interpreted as the mean of Y1, so the expected outcome in the population if everyone were treated. That's a strength, the fact that we no longer relate to standard statistical modeling in terms of defining the estimand, I would say is a strength in that sense, but it's also a potential weakness. And I'm going to go through several weaknesses that we have identified. First of all, this non-parametric approach has been really well developed for cases where we have a dichotomous exposure, but not so well for cases where we have a continuous exposure. And therefore, it would often lead people to dichotomize or categorize exposures, I think often more for mathematical convenience than necessarily to serve the scientific question. I'm going to list a few examples without naming specific papers, but all the examples relate to papers that involve expert statisticians. So the first one is focusing on what the expected outcome would be if everyone had low physical activity or very high physical activity, or what if everyone had normal weight or were obese. I think these are very ambitious questions to try and identify or to try and find the answer to, because it's very hard to imagine a population where everyone would be very physically active or where everyone would be obese. And in that sense, I think even though we have a fairly simple estimand, maybe we are being a bit overly ambitious and not necessarily answering the right scientific question. There's been some attempts to handle continuous exposures also in this non-parametric framework, but also that has sometimes led to rather asking dubious questions like, what if everyone had a BMI of 25? I think is a very ambitious undertaking and maybe not precisely the most interesting scientific question. What if all pregnant women smoke during pregnancy? Well, also here, I would say it's maybe difficult to imagine a world where all pregnant women smoked, and sort of calling for maybe refining the population on which we want to learn about the effect of smoking. In a time-varying context, there's often a focus on what if everyone would be continuously treated, or what if everyone was never treated. Again, these can be difficult questions, or maybe ambitious questions to try and answer in settings where over time it appears that treatment or no treatment is just not an option on the table for some people, given what we know by that time for them. So that these questions may be too ambitious, we often see reflected in extreme inverse probability weights. And sometimes I believe that gets a bit hidden by relating to weight truncation strategies, which are somewhat heuristic and may even be changing the estimands that we aim to identify in the first place. Likewise, as the analysis becomes more complicated, for instance, when dealing with a continuous or a time varying exposure, it's very common that we sort of move away from our initial aim to come up with a non-parametric estimand, but we fall back into standard statistical modeling. For instance, in causal inference, it's fairly common to relate back to logistic or Cox marginal structural models. And the fact that we sort of fall back into standard statistical modeling brings back also the problems I identified at the start of the talk. I think the previous examples suggest that this hygienic thinking, if you like, about starting the analysis with a non-parametric estimand doesn't always easily translate into practice. We can do better. We can also focus on other types of interventions, like what would be the effect of a particular shift in the BMI distribution, or we might try and learn the effect of a certain dynamic intervention, where whether or not we treat a certain person depends on the health status of that person at that time. We might restrict the population, like the subgroup of pregnant women for whom we evaluate the effect of smoking during pregnancy. Maybe we can refine the analysis to women who are at risk of being both smoker as well as non-smoker. We can all do that. We can refine the analysis. But that brings many other questions. What shift intervention should we focus on? How should we restrict the study population? These are useful questions, but they're also difficult questions that don't come with a necessarily a very simple answer. And even if we answer them, the ambitious nature of those questions may eventually lead us back to relying on inverse weighting by densities, especially when focusing on a continuous exposure like BMI, or give rise to inverse probability weights with large variability, which again brings some concerns. I'm certainly not claiming that those analyses are not useful, quite on the contrary. I do think that these specialized analyses are very useful, and we certainly don't mean to offer a substitute. The point I'm trying to make is that these analyses can also be demanding. They may require that we sit at the table with different parties, with statisticians, with clinicians. And in that sense, these analyses can be very demanding in terms of delineating what kind of interventions do we want to focus on, what kind of population do we want to focus on. I do believe that these analyses need care, given that they may easily lead us to focus on overly ambitious questions like, what if everyone were obese? So in this work, we've therefore chosen to set a step back, and the key question that we will try to address is, can we somehow use generalized linear models only with the aim to summarize main effects and interactions, but while still properly handling the curse of dimensionality? We've explicitly chosen to focus on generalized linear models because it's a very popular class of models, and by focusing on those and trying to prove what people now do in the context of generalized linear models, we hope that we can improve the quality of routine analysis that happen on a very large scale. On a very large scale without necessarily the involvement of expert statisticians. Again, I do think that the causal analysis where we focus on a more targeted, specialized estimand remains useful and will often even be more useful. But I do think that will often involve the expert statistician as well, and we don't often have that luxury. Also, we believe that in choosing an estimand, trade-offs need to be made. The estimands that we would like to identify from a scientific perspective may be too ambitious, given what the data allow us to tell, and in that sense, we must often navigate between interpretability versus variance. What we ideally would like to estimate is maybe not what the data allow us to do, and in that case, we need to basically step back, which is really what the proposed approach will try to do. So let me give you a snapshot of what the approach will be like and what features we wanted it to have. So, as I said before, I'm going to propose an approach to estimate main effects and interactions in a generalized linear model, because this is what many people tend to focus on today, and we hope to improve what people do currently in practice. It's going to run flexible modeling or even machine learning in the background in order to prevent bias, but the inference providers is designed to be valid and will be asymptotically at least valid in spite of the use of model selection or machine learning procedures. And it's also going to be valid even when the generalized linear model that we use is misspecified. We only use, again, the generalized linear model as a way of summarizing effects and communicating effects, but we're not really going to rely on it being valid. So to give you a quick idea, if we have a dichotomous outcome, then we may explicitly choose to work with a log link instead of the usual logit link, just because it helps the interpretation, which we can then make on a relative risk scale. And we may deliberately choose to leave out interactions between exposure and covariates, again, because the focus may be on the main effect itself. We wanted the approach to connect well to real applied practice, and that's why we've chosen to focus on generalized linear models. In fact, the approach will work as such that the parameters that we estimate, they will have their usual interpretation when the generalized linear model is correct. And that interpretation will remain safe. In fact, we've designed the approach so that that interpretation would remain safe if the model is misspecified. And I'll clarify exactly what I mean by this later in the talk. The approach has essentially the same flexibility as GLMs in that we can handle continuous and dichotomous exposures in the same way. And we also wanted the approach to avoid gross extrapolation because we were aiming for something that we could make broad or widely available, say. So the use of inverse weighting by densities is something that we really wanted to avoid. So I'll explain how we construct an estimand, and I'll talk a bit about why we made specific choices, basically. And then Oliver will focus more on estimation and raise a few discussion points. So the key to a solution in terms of separating modeling with the aim to summarize from modeling in order to do confounding adjustment, or more generally to address the curse of dimensionality. Well, the key to the solution is really to separate those two. And one way to do that would be to project the distribution of the data on a semi-parametric model. And that has been done by many others before. But there's a few drawbacks. First of all, it's good to realize that this projection approach, although technically feasible, is not very often done in practice. And hopefully we can make that happen more with the current work. But also the usual projection approach sort of gives up on interpretation almost completely. We may have no good understanding if we project the data distribution on a model, exactly what estimand that delivers, or if you like, how the different observations are sort of weighted to produce a number at the end of the day for the association between exposure and outcome. We don't have a very good understanding of what the estimand represents, even whether it really captures the association of interests is not something that we can easily understand with this approach. And I'll give you an example to illustrate this. With the dichotomous exposure and the linear regression for the outcome, working along the lines of projection with ordinary least squares basically leads to the following estimand for the slope beta, indexing the exposure here. So the first term is a mean difference in outcome between treated, say, and untreated people with the same covariates. They are weighted in a certain way. And so that term tells me something about the association between exposure and outcome. But the second term contrasts the true probability of being treated, given L, with an approximation of it. Pi tilde of L is a least squares projection of the exposure on the covariates. And so this has more to do with the extent to which the probability of being treated follows a linear relationship with the covariates or not. That's disturbing. It means that the estimand for beta that we obtain with these projection arguments is complicated. It would be much more complicated if a nonlinear model were used. And more worrying is that it's no longer even summarizing, or at least no longer even guaranteed to summarize the association between y and a given L. So what will we do instead? Well, in each covariate stratum, we will summarize the association of interest by basically using a population least squares regression of the expected outcome. In fact, for the moment, I'm imagining we have infinitely many data. I'm only trying to define an estimand here, and Oliver will later talk about estimation. But if I had infinitely many data, I could take the expected outcome given exposure and covariates on the scale of the length function and regress that on the exposure. I can do that in each stratum separately. Let me call the regression slope beta L. Then eventually, across all strata, we get to see a whole distribution of association measures, beta L, and we will summarize that distribution in terms of the central location. We focus on the central location such that whatever summary I'm going to come up with will equal this parameter beta in this GLM, where G is a length function, if this model were correctly specified. But again, the approach is not necessarily asking for that model to be correctly specified. But if it is, then what we attempt to estimate will agree with this parameter. So as a way of identifying central location, we've chosen to work with a weighted average of these stratum-specific effects with non-negative weights, largely because weighted averages are reasonably easy to communicate and interpret. For instance, with a dichotomous exposure and outcome, and if we're using a log link, then we basically obtain a weighted average of log relative risks. And in that sense, I would say that if we naively interpreted the estimand beta as a log relative risk, well, then that's still reasonably safe because it's only a weighted average of log relative risks. So in that sense, the usual log relative risk interpretation would often be reasonably safe, and we would not necessarily ask our clinical collaborators, if you like, to completely understand this more subtle interpretation. I think in many cases, the usual interpretation will be reasonably safe. How do we choose the weights? Well, we've chosen to use weights proportional to the exposure variance for multiple reasons. First of all, this is relatively simple. The weights that we work with are, for instance, not dependent on the choice of outcome or length function, which is kind of nice because it makes the estimand easier to communicate. It's pretty safe. We've chosen the weights in order to prevent extrapolations from happening, as may happen when asking overly ambitious questions. For instance, these weights are going to eliminate strata from the population where the exposure is not varying, and so where there's nothing really to learn about the exposure effects. And so from a more theoretical perspective, using these weights will prevent the need for inverse weighting by the exposure density, which could make the analysis rather unsafe to use on a wide scale. I think the weights are relevant if we are interested in the causal effect of the exposure. Well, then again, I don't think we are so much interested in the effect of exposure in those strata where the exposure is not varying a lot, because those are probably the strata where the clinicians know what treatment to assign. Like in intensive care, if we look at the effect of renal replacement therapy, there will be many patients for whom renal replacement therapy is not an option on the table. And so for them, the treatment choice is not going to be varying. And so we basically eliminate those patients from the analysis. And finally, interpretable. You could also interpret the estimand beta as an unweighted average of the stratum-specific effects, but then it must be interpreted relative to what I'll call a target trial, not in the sense that Miguel Hernan defines it, but in a more rough sense, I would say, where a trial of individuals recruited from the study population with the probability of recruitment being proportional to that variance, and with a dichotomous treatment that would be proportional to the chance of being treated as well as the chance of being untreated. Of course, we don't use those recruitment probabilities formally in practice, but I do think that this weighting may well deliver a population that is reasonably close, hopefully, to the kind of trial population we would get to see if you were to ask clinicians to recruit patients into a trial. They would obviously not recruit patients for whom we know quite well what treatment to give. And I think these weights are sort of eliminating those patients. Also, the characteristics of that target trial population can be summarized because we sort of reweighting patients in the study population, and so we can see what the average age and so forth would be in that target trial population, so we can develop an understanding of who we are talking about. We've chosen in the framework not to downweigh strata with large outcome variability, as may be needed to handle heteroskedasticity, because we feel it's maybe less likely that if you were to ask clinicians to recruit patients into a trial, that they would be taking into account outcome variability when making such decisions. In summary, with the chosen weights, the estimand basically reduces to the expression here, and this estimand has received some attention in the literature when G is the identity link, but so we're generalizing this to arbitrary link functions. We've also extended the work to effect modification. I will not really say or already talk about this, but I think the biggest challenge that we found there is to prevent, or let me put it differently, to find an estimand where the estimation strategy would not invoke inverse weighting by densities. And I will refer to the paper for the details on that. Before handing over the word to Oliver, I just want to use 2 more slides to say a bit more about one drawback of the proposed estimand. In fact, we found that coming up with a model-free definition for beta for this generalized linear model parameter, we found that not to be all that obvious. In actual fact, there's infinitely many choices you could come up with that may all reduce to this parameter beta when the generalized linear model is correct. And so finding a good summary, if you like, was a bit of a challenge. One drawback of the proposal in the paper that will appear from Oliver's part of the talk is that it can be difficult to infer when the derivative of the link function evaluated at the expected outcome gets large for some subjects. And that's related to the fact that we are sort of ignoring issues of heteroskedasticity in how we define a summary measure. Choosing weights to accommodate heteroskedasticity would sort of be the obvious way out, but I think that would complicate interpretation, as I was alluding to before. We've chosen the weights so that they could be linked to a sort of target trial that's hopefully reasonably sensible. So to account for heteroskedasticity, we believe we should seek a remedy in redefining beta L. And so the kind of thinking we are going through now is the following. We see value in redefining beta L as the value that sets the expected efficient score under this generalized linear model, but a model with stratum-specific coefficients. We can redefine it as a value that sets the expected efficient score under that model to 0 in the stratum of individuals with covariate L. So again, I'm thinking about a setting where we have infinitely many data. Then in a given covariate stratum L, we can look at the efficient score in this model where there's one slope and one intercept, if you like, and then define beta L as the one that sets the expected efficient score to 0. That assures, because we do the regression in each stratum separately, we have a guarantee that it's capturing the intended association, and I think this would only be complicating the calculation of the efficient influence function, but not really giving up on the interpretation, because we keep on reporting like the same weighted average of stratum-specific effects with a slightly different definition. I'll hand over the word to Oliver now, who will talk about the estimation strategy and some discussion points.
Thank you very much to Stijn. So Stijn's described the proposal we give for a main effects estimand. It's model free in the paper, and I'll now discuss how we will estimate it from a given data set. So one way that's quite it seems natural is just to look at the sample analog of this estimand given at the top of the slide. So the sort of empirical analog at the bottom involves several conditional expectations that we will usually not know in advance of seeing the data. And of course, we're going to try and estimate these. So in the spirit of being Assumptionlean, one might use flexible data adaptive methods such as machine learning techniques, and then plug estimates of these quantities into this formula at the bottom. So I can refer to the resulting estimator as the plug-in estimator. Now, this has some sort of intuitive appeal, but it actually is not a great idea in terms of developing estimators of our target parameter, which have good properties. So why do we not like plug-in estimators? Well, they suffer from plug-in bias. Now, the data adaptive estimators that we use for the nuisance parameters, so these conditional expectations, are tuned generally for optimal prediction in a new sample of individuals with similar characteristics to the training sample. However, this is usually balancing bias and variance in a way that makes the bias too large with respect to our estimator of the target of interest. So the bias is larger than we might like. The second issue is that the convergence rate of these estimators of the nuisance parameters, if we're estimating them data adaptively, is usually going to be too slow for parametric rate inference. So that the variance may not scale as 1 over root n. So the slow convergence rate is usually picked up by the estimator of the target parameter. Now, one might say, well, okay, I'm happy to be more flexible and give up on parametric rate inference. But the question is then, well, how do we account for the uncertainty in the estimation of these nuisance parameters? So we usually don't, the statistical properties of these data adaptive estimators are usually poorly understood. And it's therefore uncertain how to calculate good standard errors for the plug-in estimator. The bootstrap seems like a natural choice, but in general, it has no justification because of the lack of regularity of the data adaptive estimators. So the key insight from the mathematical statistics community is that the estimator's plug-in bias is primarily driven by the sample average of the estimand's efficient influence function. So Stijn has already mentioned the efficient influence function, and it's really key in our proposal for inference. Because by calculating the efficient influence function, we can then approximate the bias, the plug-in bias. And specifically, an estimator that does not suffer plug-in bias can be obtained by essentially setting the sample average of the efficient influence function to 0, so using it as the basis of an estimating equation. And this is not a new insight in our work, but is really the principle behind the recent work on double machine learning in econometrics, and also the work on targeted learning and TMLE. So bringing this back to the estimand we propose, the estimator which sets the sample average of the efficient influence function to 0 is equal to this quantity that's given at the top of the slide. So this estimator is given in closed form here. So it's very closely linked to this estimator from this work of Robinson for the partially linear model. It's very well known in econometrics. Sort of generalizes this to nonlinear models. So we refer to it as a generalized Robinson estimator in the paper. And this estimator that sort of corrects for the plug-in bias involves quite a few unknown expectations now. And again, we propose to substitute these by estimates. So we've talked about how to remove plug-in bias. The question is, well, then how do we account for the uncertainty in how we've estimated the nuisance parameters? Well, the key property of an estimator based on the efficient influence function is that it behaves Similarly, in large samples, to an oracle estimator, where the nuisance parameters were known rather than estimated from the data. Okay. So the fact that our estimator is behaving in a similar fashion to this oracle estimator, where the nuisance parameter is known, means that we can do inference pretending that the nuisances were known rather than estimated. We actually get a very simple formula for calculating the variance of our estimator based on 1 over n times the sample variance of the influence functions. And we pretend that the conditional expectations were given rather than estimated. This result is very convenient because it's not dependent really on which data adaptive estimators we choose for the nuisances involved here. It's the case whether we use simple parametric regression or even more black box machine learning algorithms. Okay, so I think this is a very nice result, but of course there are several caveats to discuss. So the first caveat is that when we're using very flexible sort of data-hungry machine learning methods, then in order to deal with bias due to overfitting, in general, we need to use sample splitting or cross-fitting to get valid tests and confidence intervals at the end of the analysis. So usually we want to estimate nuisance parameters on a separate sample from the one that we estimate the target. Furthermore, strong smoothness and sparsity assumptions may be required in order for the learners of the nuisances to converge sufficiently fast. So the standard rate in the literature given is faster than n to the quarter. And these assumptions can be sometimes very, very strong when the covariates, when the dimension of the covariates is quite high. So earlier on in the demo, I gave some simulation results. We saw that our estimators and intervals did well in terms of bias and coverage. When the model, under model misspecification, they did pretty well in terms of efficiency relative to the gold standard MLE when the model was correct. But when the data generating mechanism was very complicated, we saw that often the coverage could be pretty low in small samples. And this was reflecting the fact that we were using random forest estimators, and these were perhaps very far from the true conditional expectations. So for these reasons, we've called our paper Assumptionlean rather than assumption-free inference. So we believe that the proposal has the potential to improve standard regression modeling, even by non-experts or non-statisticians. So firstly, it avoids the trade-off between correctness and simplicity by separating the assumptions used to form an estimand from the assumptions that are used to deal with the curse of dimensionality. So unlike other types of projection parameters, it's guaranteed to summarize the association of interest. It addresses the ignored problem of post-selection inference. So suppose that we're lucky enough to use our data to select the correct model. Well, the problem is then that if we're lucky enough to have found the correct model using the data, that the resulting standard errors are usually don't honestly reflect the uncertainty in the analysis and are not generally valid. So using our approach, we start off with a pre-specified estimand, and we can bring in variable selection whilst still ensuring tests and confidence intervals at the end of the day. Furthermore, when the model is arbitrarily misspecified, the inferences are still valid. It enables the use of flexible automated algorithms that we can pre-specify in our analysis protocol. It doesn't attempt to infer the entire data generating mechanism, but is rather tailored towards the association of interest. So although the underlying theory and the use of the black box methods for nuisance estimation may seem to make things more complicated, these can, by the fact that we can link the analysis back to a model, these complex features can largely be hidden to the end user. And because our estimands do not usually require strong extrapolation, it moreover prevents asking overly ambitious questions. Finally, it may potentially play a role in making machine learning interpretable by summarizing the machine learning predictions. So I think we want to make the point that we've tried to work towards a generic solution that can be applicable to many different data analyses, but it may rarely be the perfect solution for the problem at hand. So I think we're not trying to argue that causal inference estimands, like the average treatment effect, should be replaced. The typical causal inference approach may be preferable for many causal questions, although it, of course, may be very demanding in terms of requiring some extrapolation. Rather, our primary aim is to improve the quality of data analyses in a large number of cases where the perfect solution is not within reach. And this can also be the case in causal inference. So, for example, choosing an estimand when we're interested in effect modification between a treatment and a continuous covariate, or finding, I think, a model-free estimand is not at all obvious. So we hope that our framework may be useful for these kind of problems as well. So we've critiqued the modeling tradition for delivering estimands that only carry meaning when the model is correctly specified. But we've also critiqued the estimand tradition for giving up on modeling altogether. So in causal inference, maybe there's focus on very simple kind of questions where the nonparametric estimand is very obvious, but we feel that there's a need for availability of model-free estimands in more general data analysis. So we've made use of these so-called projection estimands, which sit somewhere in between the modeling and the estimand traditions. But in comparison with other work that's been done on these projection estimands, we hope ours retain a useful interpretation, or at least they're developed to retain an interpretation when the model is misspecified, and always capture the association of interest. So more work is needed, of course, for this to happen for other model classes. So we've made a start by focusing on GLMs, which are kind of underpin statistical education and practice. But of course, the proposal could be extended to Cox models when proportional hazards is violated, repeated measures models, but also examples in causal inference where we end up relying on statistical modeling again in order to provide a summary. So in cases in mediation problems or with time varying confounding. So we've tried to make a proposal in terms of estimands that we feel could be useful, but we also hope that our work generally raises the discussion about the use of modeling in statistical education and practice. So I'll close the talk with some discussion points. So firstly, many data analyses are subject to some kind of coarsening. So this could be confounding, but also missing data, censoring in survival analysis, selection bias, measurement error. And in a parametric regression framework, under a so-called coarsening at random assumption, we can ignore the coarsening, both in terms of how we define our estimand, but also how we do inference because of how the likelihood usually factorizes. Now, I think there's increasing awareness that when a parametric model is wrong, then likelihood estimators usually end up targeting estimands that depend on the coarsening mechanism. Now, these estimands can often be inferred quite precisely from the data, but they're not necessarily ones that are of scientific interest. They may be difficult to communicate and compare between different studies. So it seems appealing to target estimands that do not depend on the coarsening mechanism because of to facilitate easier interpretation. So we acknowledge in our work, we've deliberately chosen to let estimands depend on the exposure mechanism. And this was due to the fact that we tried to develop estimands that are that work for all types of exposures. And this was an inevitable consequence of that. But the question is, if we look to estimands that are free of the coarsening mechanism, what if this requires too much of an extrapolation? So these type of types of estimand are generally going to be much more ambitious to infer, and it may not make sense to look at them in cases with very strong coarsening mechanisms. Should we then go for a less ambitious estimand, but which is much harder to interpret? The next question is, well, how practically feasible is this? Should all types of coarsening be treated the same, or is censoring different to missing data in how we choose our estimand? So to give an example of this, well, suppose we have non-monotone missingness in the covariates L. In that case, a non-parametric missing at random analysis can end up becoming very complicated. The use of inverse probability of missingness weighting ends up becoming quite complex. An analysis under the complete case assumption that I give on the slide here, where R is the missingness indicator, may be much more plausible than, or I should say that R is equal to 1 if someone is a complete case. So this assumption may be much more plausible than the usual missing at random assumption. But the estimands that are then natural to target under such an assumption may be dependent on the conditional variance of A, given that 1 is a complete case and the covariates L. So in having estimands that depend on these weights may be much more harder in general to communicate and compare between studies. So the next point relates to double robustness. So we've delivered estimators for parameters in generalized partially linear models, but estimators for this parameter beta that have been constructed, which unlike ours have this double robust property. Now, in the setting that we're using like nonparametric or flexible estimators of the nuisance parameters, this has the advantage that one can usually or often weaken the end-to-the-quarter rate requirements that I referred to earlier in the talk. So, for example, an estimator of the conditional mean of y can be allowed to converge very slowly to the truth if we have fast convergence of the propensity score, and it can be this conditional mean of y can be very slow when we know the propensity score is in a randomized trial. So this property that we can relax trade-off assumptions on the nuisances in this way was described as rate double robustness in this paper by Smukler et al. However, the rate double robustness property, at least in these kind of problems, comes at the expense on invoking extra parametric modeling assumptions. And when these modeling assumptions are wrong, it means that the resulting inferences may longer be accurate. This was borne out in the paper in simulation studies. So I've looked at rate double robustness here, but when we're thinking of robustness towards model misspecification, standard inference is not usually double robust here when data adaptive methods are used, although a more involved procedure for double robust inference can be used. So I think that double robustness may nevertheless be useful because we've increasingly seen that it can inspire us to construct estimators of nuisance parameters that really target high quality estimation of our target. So by high quality, I mean with small bias and variance. So whilst the work on this topic has been usually in the context of parametric models, it's now being extended to more flexible machine learning tools. So the philosophy behind our paper, I think, raises questions about the role of parametric and semi-parametric efficiency theory. So in this work, we usually start off by assuming a correct model, and then we say, well, given that the model is true, what's the estimator I can find that has the smallest asymptotic variance among regular and asymptotically linear estimators? But the question is it really right that we trust this model to be correct? And why do we want to extract information based on model assumptions that may not be supported by scientific knowledge? I think there's kind of a paradox here with respect to traditional efficiency theory, that the correctness of the model becomes more plausible if we can say, well, it's supported by the data, but if we use the data to select a model, then in general the traditional efficiency theory no longer applies. However, again, I think like double robustness, efficiency theory still has, we still feel it has some use. But in this case, it may be useful in terms of suggesting nonparametric estimands. So it may help us to learn the type of estimands that can be estimated precisely from data, even if these are not the ones we choose to target. Final point is that our estimands involve averaging over the distribution of L and sometimes A in order to provide a summary of association. Now, it's not always clear that these kind of summary measures are useful or easy to interpret. So suppose that a treatment is harmful for half of the study population but is beneficial for the other half. Well, does it then make sense to report a weighted average of the conditional effects? In time to event settings, the hazard ratios may change direction over the course of follow-up. So does it then make sense to report a weighted average of log hazard ratios? For continuous exposures, our estimands essentially aim to capture a conditional linear association on a relevant scale. But if on the chosen scale, if our exposure A has a very complex nonlinear association, is it really useful to even report a single numerical summary? So I think there's value in supplementing a summary estimate, which may be helpful for an abstract of the paper, with a more fine-grained description of the data. And this might be done using ideas from nonparametric statistics. So in future work, we plan to evaluate these kind of continuous summaries. So for example, in the case of a continuous exposure, one might target the kind of estimand I give on the slide. And I think that the results can then be summarized visually using a curve, ideally with confidence bands. And I think this is a very interesting statistical problem as well, because we're now targeting an infinite dimensional parameter where we also have nuisance parameters to estimate. So optimal estimation and inference for this kind of problem, I think, is a really exciting area of research. So with that, I'd say thank you very much for everyone listening. Thank you very much for the invitation to present our work, and I'll now hand back over to the chair.
Thank you very much, Stijn and Oliver. I'd like to now call on Rhian Daniel from Cardiff University to propose the vote of thanks.
Okay,
Great.
Thank you very much. So it is an enormous honour and pleasure to propose the vote of thanks for the paper that we've just heard so beautifully presented by Stijn and Oliver. I truly think this is a wonderful methods paper. Why do I say this? Well, it proposes a novel way of analysing data that constitutes a substantial improvement on what was available previously in many different respects. And you might think, well, shouldn't all good methods papers be attempting to do this? And of course, yes, but they certainly achieve this very strongly. And as in fact they've been describing, they do so while avoiding the luxury dog's kennel trap. You may know what I mean, that feeling when you're reading a methods paper and you feel that the authors are somehow trying to lure you to leave your modest but practical suburban semi-detached house and move to a luxury dog's kennel, in the sense that maybe their method has aspects that are really state-of-the-art, but other aspects that are entirely impractical, perhaps because continuous predictors can't be accommodated, for example. So Stijn and Oliver, that by starting from the generalized linear model and building on that, as they've so beautifully described, they really retain all the convenience of what we usually do and just build the state-of-the-art elements on top of that. So that's very, very nice. I also really loved the way the paper was written, because there are lots of technical subtleties in there, but they somehow introduce them in a way that makes it really obvious why you need these things, but at the same time without really dumbing anything down. So you sort of really feel that you are acquiring the kind of understanding that they have by the way they explain things so beautifully. And I think it deepens our understanding, therefore, because of the way it's written, even of the parts that maybe were known to us already. But for me, at least, it also corrected my understanding of things that I thought I had understood, but hadn't really. So my brief remarks now, I'm going to attempt to expand a little on this. But first of all, just a brief summary, not that we really need it because Stijn and Oliver have done such a wonderful job, but just a brief summary of the comparison of philosophies that they give in their paper. So the traditional approach is to start from a parametric model and then to perform estimation, inference, and even the interpretation of beta under the assumption that the model is correctly specified. And of course, we may worry that if A is continuous, for example, that the effect may be nonlinear or that there may be product terms needed. And the usual thing that we say to ourselves to reassure ourselves, I think, is, oh, well, even then, the beta hat that we estimate is still targeting some kind of an average, isn't it? And of course, in their paper, they show that this is not necessarily the case. Of course, in practice, this is not what we do. We probably do look to the data to see if there are nonlinearities and product terms needed. But then, as they've explained so beautifully, the standard inference then is compromised. And then on the other hand, we have the causal inference philosophy, which is to start from an estimand. And of course, usually the exposure that in the sort of examples where the settings where this is applied, the exposure is often binary, so a treatment. And it makes sense scientifically, perhaps then, to ask about a marginal effect of comparing treating everybody versus treating nobody. And of course, effect modification may come in, but again, usually in a sort of binary sense, so maybe, or at least in a discrete sense. So we may ask what's the effect in women versus in men. And these sort of simple estimands then are, their interpretation is model free, which we like very much. And for the estimation of them, they can then be based on parametric nuisance models. In other words, this model may come back again, but now as part of the data analysis rather than as part of defining the estimand of interest. Or indeed, we can do away with the model and adopt something more flexible. And I think it's widely understood that if the model is too simple, then that risks bias in our estimator of the estimand of interest. Whereas if we are perhaps more flexible than we need to be, then we may have increased variability. And then the literature on targeted learning and the related literature from other fields has brought to our attention that if we are very careful in our choice of estimator, then we can achieve this really quite remarkable property that Oliver was talking about, which is that we can achieve quite simply honest inference even after model and variable selection and machine learning and so on, which is all very, very nice, but has been somewhat less well developed for continuous exposures and effect modifiers. So enter Stijn and Oliver. So their philosophy, as I understand it, is to be motivated by a model, such as this one, and then to consider an estimator beta hat that's consistent for beta if the model is true, but then to ask what's the probability limit of beta hat under no assumptions, and call that beta star. And that's really the estimand. And we can look at it and see, well, is it some sort of an average? And if not, back to the drawing board. If yes, then they ask really quite a demanding question. They ask, is consistent estimation and honest inference about beta star possible under minimal assumptions, even after model or variable selection and without density estimation for any continuous variables? And I think this is a very high demand, but one in the paper and now in their explanation of their approach that they argue very effectively for why this is indeed the kind of high standards we should be asking of our data analysis. In other words, they're asking, can the data speak practically and honestly to beta star? And if not, then we should go back to the drawing board again. But of course, in their proposal, they show that the answer to both of these questions is yes, even for continuous exposures and effect modifiers. In other words, they are taking the best of both worlds. Yes, they start with a model, but in fact, it's a semi-parametric model that makes things work. But they give a model-free interpretation of beta that, yes, is some sort of an average, but then they can estimate it flexibly. They have this honest inference property, and it's naturally accommodating of continuous exposures and effect modifiers. So when I was reading this, it made me reevaluate what I think my understanding has been previously of what we talk about the bias variance trade-off in statistical modeling choices. So I think it's often said that a simple model approach, a standard simple model is a good choice on the grounds of the bias variance trade-off. In other words, we know we're making strong assumptions because the model may not be correct, but by paying that price of that assumption, we buy ourselves efficiency in the estimators of the parameters of interest. But what I think the paper by Stijn and Oliver makes so exceptionally clear is that this is conflating the use of the model in two entirely separate ways. First, to define the parameter of interest, and second, as an expression of the assumed observed data distribution. So they also make the point, of course, that we trade off not only increased bias, but also lack of interpretation for the precision we gain when opting for the same parsimonious model in both. But also, I think I'm right in understanding that the gain in precision comes really more from the parsimony in the definition of the estimand than parsimony in the data analysis, at least up to a point where we, of course, hit the curse of dimensionality at some point. But up until that point, the main gain in precision that comes from parsimony is due to the parsimony in the definition of the estimand. And just to illustrate that, I very quickly show you some simulated data where the true data generating model for y given a and l as a function of l is the same function of L. It does depend on L, but in a way that remains the same for small values of L and large values of L. The functional form is the same. But in the data analysis, I'm going to consider dividing L up into increasingly more and more bins, and then needlessly, if you like, estimating the correct model separately in each bin, even though I don't really need to do that. And then asking, how does this decreasing parsimony, this increasing complexity in the data analysis affect the standard error of the estimators of first a parsimonious, but then a stratum-specific estimand? And this is the kind of picture that you typically get. So as the number of bins increases, we move to the right of the picture, you see the standard error of the average treatment effect increases very slightly, but the standard error of the stratum-specific treatment effect increases far, far more. So there's nothing really profound here. Of course, we know that if we keep asking more and more refined questions, which is what the green line is doing, and asking about the treatment effect in one tiny bin, then of course our precision for that estimator becomes worse and worse as we look in more and more in smaller and smaller bins. But the same thing is happening in the estimator of the average treatment effect overall. It's just that we average out all that imprecision by focusing on a parsimonious estimand at the end of the day. So this, at least in my understanding, illustrates why we can be happy that Stijn and Oliver opt for such flexibility in their data analysis. It's because their estimand is still parsimonious. It's a bit like rounding a number, but you sort of have to be careful that you're only rounding the number at the end. If you round the number too early and then do lots of calculations, you propagate errors. And I think that's a useful analogy for what's going on here, if I've understood correctly. So their parsimonious estimand is interpretable and consistently estimated under the nonparametric model. And we should view their choice of estimand, therefore, as representing a trade-off between sort of bluntness and variance, not bias and variance. So a more nuanced or less blunt understanding of the effect of A could be gained by choosing a less parsimonious summary, but at a cost of increased variance. So this hopefully now corrected understanding for me of what we sacrifice for improved precision is one example of the many, many thought-provoking insights that lies in this absolute gem of a paper. So I conclude by enthusiastically proposing the vote of thanks. Thank you.
Thank you very much, Rianne. I'd like to now call on Vanessa Dideles, the University of Bremen in Germany, to second the vote of thanks.
Thank you very much. Let me share the slides. Okay, can you see the slides?
Yeah, I can see those, Vanessa.
Okay, great. So it's a really great honor to discuss this paper by Stijn and Oliver. And I should say, as full disclosure, that I've discussed this work with them on several occasions before. And in fact, they have preempted quite a lot of my comments. So I like this work very much, but as a seconder, I'm supposed to criticize it. So I'm going to try and do my best at this. So let's just remember what is the problem, what they are addressing. Statistical inference, as we all know, depends not only on the data, but on the model assumptions. So we want to choose our models so that they represent the data. We do this in a data-driven way. And remember that we often make a point, you probably know this from your own teaching, that certain model assumptions are testable, we should check them, etc. We do all these things. But then inference must take data-driven selection into account. The model can still be wrong. Well, I should also say often the inference just doesn't take the data-driven selection into account. And the selected model can still be wrong. The meaning of the estimated parameters is then unclear. And so the proposal aims to avoid all this, at least for some estimands. So what does the proposal do? It says, let's focus on estimands, not on models, and of course, particular estimands. And I really like this. As several points have been made now, and the causal inference literature focuses a lot on estimands and maybe not even enough on modeling. So the proposal is, let's look at a class of estimands inspired by GLMs. Let's base the estimation on the efficient influence function, and then inside that use data adaptive choices of the nuisance aspects, so that the estimands are still sensible under misspecification, and so that the inference is still valid post-selection. And in a way, to me, even though I believe the math, etc., the influence function aspect and the fact that inside this you can do the data adaptive procedure and still get valid post-selection inference, to me this is still a bit of a miracle, and is probably the technical aspect and contribution of this paper. When I first heard about this work, what I had difficulties with was the estimand, the reason for choosing this estimand. So in causal inference, we have come a long way to understand the importance of choosing meaningful estimands. We think a lot about this. We do sit down, as Stijn was saying, with the medics and think through what is sensible in view of the research question at hand. Estimands that can be specified in terms of a hypothetical target trial. And I've noticed that Stijn or Oliver did give a justification in terms of a slightly strange target trial for their estimand. We like marginal causal effects. They give a certain comparability, especially in the context of collapsibility or non-collapsibility, also in terms of time varying, confounding, dynamic treatments, etc. So this is, there are some nice properties here. We might want to look at effect of treatment on the treated, risks instead of hazards. Again, Oliver mentioned this a little bit at the end. And the literature has moved towards looking at effects of nudging or shift interventions instead of these deterministic interventions. Like Stijn was saying, it's difficult to think of an intervention where we force someone to have a body mass index of 25. But the proposal obviously emphasizes and focuses on other considerations, not these types of considerations of what is it in our research question, in the problem at hand that we want to estimate. What is our estimand? So we are, for the main effects, we are faced with this is the estimand, this weighted average. I would think, even if Stijn says it's maybe easier than you think to explain to your collaborators. I would think this is not so easy to explain to my epidemiologic collaborators. It depends on the distribution of the treatment. It's an average over conditional things, which if we want a marginal effect and there's non-collapsibility is a little weird. It is, of course, reassuring that if the GLM that we started with is correct, then this is a familiar parameter. In the binary case, this boils down to this, and I find this a little easier to maybe explain. So a weighted treatment effect where the most weight is given in the regions with highest probability of being either treated or untreated. So we give less weight to those that are unlikely to not be treated or to be treated. And this, I can sympathize a lot, though maybe these are the regions where we do want to know maybe a bit more, even exactly the kind of difficult patients where we want to know more about the effects. Of course, this is easy to interpret in the binary case, but the proposal, as we also heard, is mainly aimed, maybe not mainly, but also aimed at continuous exposures where we don't want to weight with the inverse of a density. So let's think about the usual marginal effect as opposed to this weighted average. The marginal effect, the average causal effect, might be conditional on some basic baseline variables, but it's of course implicitly or explicitly also averaged over anything in the distribution that might be an effect modifier. And which distribution are we talking about? It's the distribution in the population from which the sample is drawn. And in a way, this is also quite arbitrary because really, when does our population from which we draw the sample is really representative of something meaningful? Either we have a randomized trial and the population in the trial is not really representative of the eligible population for the treatment, or it's an observational study where we rely on volunteers, and again, we don't really know what they are representing. And of course, these things have been discussed, internal validity, transportability, etc. And these, so the proposal is different from this, is maybe trying to solve this. I'm not entirely clear of how the relation is between this, so maybe you could comment on this. One of the things that Stijn says was that the weighting avoids the scientifically irrelevant question of comparing treatment and no treatment in people who will not be eligible for this. But we do still want to be aware of this. So with the proposal, will it alert us to areas where this is the case, for patients where this is the case? Like large weights, when we do inverse probability weighting, large weights will alert us to these sort of problems. Another issue that I have is about the role of the covariates. In GLMs, it would maybe be desirable, maybe there is a need for more clearer distinction between the aims of the analysis: prediction, where we throw everything in that is relevant for the prediction, and which is very different from counterfactual prediction, which is what we do in causal inference, or whether we want a specific parameter, an interaction effect or main effect here. So what is the role of the covariates? Mostly, I think Stijn and Oliver were thinking of them as confounders, but that is not always what we use the GLMs for. When we use them for prediction, we throw everything in. They can also be effect modifiers, and that's not the same as confounders. Effect modifiers may or may not be confounders, and the other way around. And as I said, in GLMs, we usually throw in several explanatory variables, and they aren't clearly separated in one treatment and the rest. So if I'm not entirely clear with their approach, is it on the causal side, is it trying to combine the causal approach and the general modeling with lots of explanatory variables approach? I think Oliver said we need to do a separate analysis for each exposure, and maybe this needs to be highlighted a little more. It might not be clear to everyone that that is what the proposal entails. I think I'm running out of time, so I'm just stop with some specific questions. Is the estimand chosen? How much is it based on the scientific question or not? There was a lot of appealing to familiarity of GLMs and the robustness aspect, of course. It seems that we cannot pick an arbitrary estimand and then use an approach that will give us the properties that we want. So what are the key properties of the estimand that it needs to have? And as I said on the last slide, what is the role of the covariates in the model? So, of course, there's this old debate between can we let the data speak for themselves? There was this promise and hype, of course, around the big data revolution, etc. Or do they not speak for themselves? Data never speak for themselves. It's the questions we pose and those we fail to ask, as well as our theory, concepts, and ideas that bring meaning to statistics of all kinds. Maybe you could say something about where you position yourself in view of your work on this dichotomy here. Thank you very much, and I gladly second the vote of thanks.
So thank you very much, Vanessa. So the vote of thanks has been proposed and seconded. I'd like to thank all of the presenters, and can I suggest that you might like to mark your appreciation by using the clap hand emoji as a endorsement of the vote of thanks. Okay. All right, so we now move on to our discussion section, and I have 5 discussion speakers lined up ready to present. And the first discussant is Peng Ding from the University of California at Berkeley. So Peng, if you'd like to take the stage now.
This is my comment on this paper by Professor Vansteelandt and Dukes. Slide 2. I first want to say congratulations on this thought-provoking paper on statistical inference with misspecified models. It deepens our understanding of the role of models in causal inference. And I will offer 2 comments below. I think both were mentioned already by Vanessa, but I will make offer more details. Slide 3. My first comment is, are the conditional estimands useful? For binary exposure A, the proposed estimand is this conditional estimand. I call it tau conditional. It is the weighted average of the difference in means under this G scale, the transformed scale. The weight is proportional to this overlap weight. It's a variance of this binary exposure, and also it's the normalized product of pi L and 1 minus pi L. It's called overlapping in the literature, and also it appeared many times for many different purposes. With identical link GZ equals Z, this reduced to the average treatment effect for the population under the overlap weight. Slide 4. However, with nonlinear links for binary outcome Y, for example, it is a weighted average of the conditional risk ratio or odds ratio. It does not equal to the standard marginal estimate. So here I call it tau marginal. It is the difference in means under this G transformation and weighted by using the same weights. Okay, with the log link, the conditional estimate reduced to the average of the conditional risk ratio, and the marginal estimate reduces to the log of the ratio. You can see these 2 formulas are very similar, but we put log on different places and put expectation on different places, and they are different in general. And I have a slide 5 to show you some comparison of these 2 estimates in the ideal case, with a binary covariate L, and in randomized trial, A is completely independent of everything else, the potential outcomes and covariates. And I draw all the probability parameters because now everything is binary. I just draw all the probabilities from uniform 0, 1, and this is based on many Monte Carlo samples, and you can see the conditional estimands and the marginal estimand. The first figure is a marginal effect with log link. The second one is with a logit link. They can be quite different, and they can even have different signs in these Monte Carlo samples. So if you think the marginal estimands are easier to interpret, then the conditional estimands can be problematic. Slide 6. The author already pointed out the conditional estimand is different from the marginal estimand in the paper, and they argue an advantage of this conditional estimand is it reduces to the logistic regression parameter beta if the generalized linear model is correct. And the marginal estimand is not the same as this regression coefficient beta, even if the model is correct. But there are two exceptions. The first one is the identity link. The second one is the log link. The logit link does not work. But I will go further to say, even if the model is correct, the beta parameter may not be the parameter of interest, even if the data is from a randomized trial, because beta is the conditional risk ratio or odds ratio given L, but the policy relevant estimand is the marginal risk difference, risk ratio or odds ratio. There was a paper by David Friedman in statistical science criticizing the use of generalized linear models in experimental setting. Basically, his point is those parameters are conditional estimates are not of policy relevant, even if the models are correct. If the models are wrong, then it's even more difficult. Okay, this is my first comment. Slide 7. My second comment is, if we have two binary exposures, A1 and A2, oftentimes we are interested in not only the main effects, but also the interaction. So basically, we're interested in them simultaneously. In the paper, the authors proposed model 7. There's a extension of this generalized linear model for the case with interaction. It was an interesting motivation for the novel interaction measure in the paper. But if we are also interested in the main effects, that model is not so natural to motivate the main effects measures. But their section 4 indeed motivates us to define a general weighted contrast. So here I call it tau C, C for contrast. It's motivated by the paper. And this WL term is the overlap weight. And the second term, summation over all combinations of the levels of A1 and A2, the C part is the contrast and the G part is the mean. And we can define any weighted contrast we want. And again, this WL is in this form. It's the harmonic average or the normalized form of this average. It's called the generalized or general overlap with multiple treatment levels in the literature. Slide 8. With this general definition of weighted contrast, we can choose different C's as we want. If we choose C in the first combination, like 1, -1, -1, 1, it is the interaction measure proposed in the paper. If we choose other numbers, like 1/2, 1/2, -1/2, -1/2, it is the main effect under the overlap weight. It's different from the traditional definition because there is a weighting term. With C equals 1/2, -1/2, 1/2, -1/2, it is the main effect of A2 under this overlap weight. And it's also straightforward to extend tau C to the setting with multiple factors, not only 2. So there is a question. model 7 in the paper is natural to motivate the interaction measure. What is the model to motivate a general contrast, tau C? And more interestingly, if we are interested in multiple contrasts simultaneously, how do we come up with a model to motivate them simultaneously? The last slide 9. So this is also my final remark. The authors provide inspiring derivations of the novel average effect and the interaction measures under possibly misspecified models. The question is, how general is this strategy beyond these two measures? Like in the interaction case, in the factorial experiment case, it's already non-trivial. How do we think about a model for general measures? So there are many more complex settings. How do we use their strategy for those settings? Okay, thank you very much again for this inspiring paper. This is my comment.
Okay, thank you very much. I'd like to now invite Mats Stensrud from EPFL Switzerland for his 5-minute discussion. Thank you.
Go to the next slide, please. So first, I'll say that this is joint work with Arun Sarvet. He's actually continuing on this presentation, so he's doing a part 2 later on in today. So you'll see his face soon. And he's soon joining me as a postdoc in Lausanne. Next slide, please. But even before I start discussing next slide, please. Even before I start discussing the content here, I would also like to say congratulations for an innovative contribution. And once again, I learned a lot from Stijn, who I've learned from for several years, and also from Oliver more recently. Thank you very much. Next. So this talk will focus a lot on interpretation of these Assumptionlean estimates. And when you talk about estimates in the first place, you're preaching to the choir, because I'm all about estimates in the first place. But I'll build on Vanessa's points, and they will not be the same as Pang points, but they would also concern what does these estimates actually mean in even simpler settings. Next, please. So to start off with, we'll start with a data example, and that will be Oliver and Stijn's own data example. Next slide, please. So just to be clear, what they study in their own data example is a causal question. Next, please. They want to study the effect of reducing, the effect of this first steps program in Washington State, and how that affects the risk of low birth weight. So this is clearly a causal question, and in this analysis, or in this data analysis they're doing in their example from the paper, that's a binary treatment. So next, please. So we will also here, to make things very concrete and simple, to study the same example. So if I hadn't seen Stijn's paper and Stijn and Oliver's papers, I think one natural thing that many investigators, I think, would be interested in, for example, the policymaker who implemented this program, what is the average causal effect? So here we use notation similar to the original paper with superscripts denoting counterfactuals. Next, please. And under the simplest causal assumptions that also were invoked by Vansteelandt and Jukes, we can identify this parameter above, this contrast of counterfactual outcomes, as these functionals of observed data. Next, please. However, Vansteelandt and Jukes' starting point is a different one, and we have seen this expression several times now. Next, please. And we know when the model assumptions are correct, that is that the GLM model is the true data generating model, that's equal to the average causal effect. But does this estimate honestly reflect the question of interest? Well, next, please. We have already seen now from several of the talks, from Oliver and Stijn's talk in the first place, and also from Vanessa's talk, that when the treatment is binary, and here for simplicity we just consider the identity link, so we consider a simpler setup than the one studied by Pang Ding. We can map this expression below, which was also studied in detail by Robbins and colleagues in 2008 in their paper on higher order influence functions, which is the variance weighted average treatment effect. Okay. And Stijn gave an argument why this could be interesting in this renal example. One could also argue that why don't you just choose those patients you're interested in the first place, and rather than that being driven by the propensity scores. But I'll leave that for now, and let's go to the next slide. So here I'll try to get a bit more insight in the very simple data generating process. And like the authors did in the original example, we consider a simple binary treatment, a binary covariate L, and a continuous outcome. So make it as simple as possible. And we know that this proposal works in much more general settings, say with continuous treatments, but it's supposed to work in a wide range of them. So it might as well work well in these simple setups. Next, please. So I'll just suppose that the data is generated by this structural equation. So Y is just a simple function of A and L. In this case, this model, if you were a causal inference researcher or used causal inference, you would immediately see that this encodes additive effect heterogeneity. So the effect of A depends on the value of L. Okay, so let's go further. Next slide, please. That's okay. Next one. So we would use observed data on L, A, and Y to see what's going on here. So suppose first also that we had this data generating mechanism for Y from the first slide was simple, and then we just assume that the probability of L equals 1 is 0.5. Okay, half for L equals 1, half L equals 0, and the propensity score for those with L equals 1 is P. For those with L equals 0 is Q. Okay. It's easy to show under this data generating mechanism that the average treatment effect is equal to 0. Okay, next please. So let's now look at Vansteelandt and Duke's estimate in this setting. It reduces to this quite simple setup. Next please. And so it's easy to study what this thing is. So suppose first that P is closer to 0.5 than Q. So this just is a feature of the propensity scores, right? Then Vansteelandt and Duke's estimand, so we're not talking about estimation here, we're just talking about the parameter here, is larger than 0, okay? Next. And suppose the reverse is true. Suppose Q is closer to 0.5 than P, then Vansteelandt and Duke's estimand is smaller than 0. In both cases, the probability of L is the same, so you could say that the distribution of baseline covariance is exactly the same in both settings. However, the estimand, unlike the average treatment effect, which is 0, could even be larger than 0 or smaller than 0, just depending on how many got treated in the population. Next, please. So we clearly see, and this is clear also from the expression immediately, we have seen that from the previous talks, that the estimate crucially depends on the propensity score. And the question is this desirable? Next, please. Under what conditions does this estimate actually then provide insight that the investigators may be interested in the first place? Stijn gave one example, but in that example, I want to follow up and ask: is it actually, if the investigators really have before they do the analysis an idea about the subpopulation in which they're interested in the effect, why don't we confine our analysis to that subpopulation in the first place? Next, please. Sorry, I think we can stop there and then let Aaron continue. This was just a detail on the fact that in practice we may also be interested in subgroup effect, and in this particular data example there was a particular covariate that seemed to be interesting, which is substance abuse or not, where you see the where they actually did that in a different publication, and they saw that was a group where there actually are big differences. But that's just a parenthesis. That's not important for the main point.
Okay, thank you very much, Mats. So the next discussant is Aaron Sarvet from Harvard University in the USA. Over to you, Aaron.
All right, thank you. Thank you so much again. Congratulations to Stijn and Oliver for a wonderful paper, and for Mats for setting me up. Next slide, please. Okay, so I just wanted to open with one of my favorite quotes by Jamie Robbins from one of his earliest papers in 1987. And one of the reasons why I really love it is because it really kind of speaks to a process that I think is really important, which is about the interface between kind of our targets of inference as statisticians and causal inference experts and the scientific questions that our investigators are interested in. So the quote reads, "A data set is a string of numbers," and can you do next slide a few times, actually, just to avoid it? "These data represent empirical measurements. In an analysis, calculations are performed on these numbers." Next slide, please. "Based on calculations, causal inference is drawn. And since the numerical strings in the computer algorithm applied to them are well-defined mathematical objects, it would be important to provide formal mathematical definitions for, in emphasis, the English sentences expressing the investigator's causal inferences that agree well with our informal, intuitive understanding." Next slide, please. And so the way that we viewed Stijn and Oliver's contributions, at least one main thrust of it, is as an intervention on how we typically understand the relationship between estimands, assumptions, and identification. Next slide, please. So just to review, my understanding of the usual approach is that we, at least in causal inference, will choose an estimand, which is typically a causal parameter that is not directly observable. We would specify a set of reasonable assumptions that define our model, and then we can use that to deduce a functional of nuisance parameters that equals this causal parameter at every law in the model. And so that's the process of identification. And so when that functional of nuisance parameters is comprised entirely of observed data parameters, then we can fully identify that causal parameter, and we get exactly what we want. But if the functional is comprised only partially of observed data parameters under that model, then we partially identify the causal parameter of interest. And so when we have partial identification, we have bounds, and these bounds may or may not be informative. Next slide, please. So to summarize, I think Stijn and Oliver have coined a really useful term, assumption-lean, but my understanding is that the usual assumption-lean approach, in quote, they approach the problem of having fewer assumptions by fixing the causal parameter and then partially identifying its value, so getting bounds on the value of the causal parameter, but keeping fixed the target of inference. Next slide, please. Okay, but we understand the contribution in this paper as turning that on its head a little bit. Next slide, please. So their approach fixes the value. So they have a fixed observed data parameter that they call the estimand, and they partially identify that fixed value with a set of possible causal parameters, possible interpretations. And what I mean by that is it includes multiple interpretations. It could be the GLM parameter if the assumptions hold. If not, it'll be some other causal parameter in, for example, the variance weighted average treatment effect. Next slide, please. And so the kind of the crux of our question is, if this is how we look at the contribution, are the bounds that are provided by this approach, are they ever going to be informative? And if those bounds on what the possible interpretations could be always include the variance weighted average treatment effect, for example, then for those to be informative, then we need that variance weighted treatment effect to have a clear and useful interpretation. Next slide, please. So, yeah, next slide a couple more times. Yeah. Okay. So to provide an answer, we think it would be really helpful to continue to develop the stories that illustrate why these parameters in the group are interpretable and useful. So do they really map to the English sentences that express investigators' causal inferences, and do they really agree well with investigators, subject matter experts in informal intuitive understanding. And we think that answers to these questions and developing these answers would provide more weight to what's already a really innovative and provocative and technically rigorous contribution. And with that, thanks again for your attention and congratulations again to the authors.
Aaron, thank you very much indeed. I'd like to now call on Heather Batty from Imperial College London.
Okay, next slide, please. Okay, for situations in which there's uncertainty over the underlying probabilistic model, there are at least three broad approaches. One is to seek reliable inference for inference parameters, or perhaps, as the authors advocate, for quantities retaining at least a degree of interpretability under misspecification. A second is to acknowledge more explicitly the model uncertainty. And a third, loosely connected to the first, is to encapsulate uncertainty over the model in a possibly large number of nuisance parameters to be eliminated in the analysis. And this is typically by conditioning arguments or other problem-specific maneuvers. So one example is Bartlett, 1937. Another is the use of partial likelihood to evade the baseline hazard function in the proportional hazards model. And the appropriateness of each depends on context. And I'll restrict my discussion to the first two of these. Next slide, please. In fact, I'll speak very briefly about the first approach. A little more detail is in my written contributions or written contribution. It appears that first-order reliable inference for an interest parameter via maximum likelihood is possible in spite of misspecification of the nuisance part of the model, only when the interest parameter is orthogonal, in the sense of Jeffreys, 1948, to the notional nuisance parameters. And the interpretation of these notional nuisance parameters then has to be in terms of Kullback-Leibler projection. An important point is that the true model is implicit in the definition of parameter orthogonality, and this is likely to cause difficulty in the verification of orthogonality. The second-order properties are always affected, sometimes severely. Next slide, please. It could be argued, contrary to the paper under discussion, that when the effects of interest are represented by parameters whose interpretations differ according to the model used, the appropriate approach is to acknowledge the model uncertainty rather than seek inference on a quantity whose interpretation is stable, but perhaps only tangentially relevant when the assumed model is false. Next slide, please. The role of sufficiency in the assessment of model adequacy appears throughout Fisher's work. And when the ideas can be operationalized, there's no difficulties associated with double use of the data for inference on the parameters of a given model and assessment of model adequacy. So sufficiency separates the information in the data into that relevant for inference on the parameters of a given model and that relevant for assessment of the adequacy of that model. And the conclusion may be that some, all, or none of the a priori plausible representations are compatible with the data. If multiple models with different interpretations are not significantly contradicted, one view is that we should aim to report them all. And this is a point emphasized repeatedly by D.R. Cox. I'll give the references in my written contribution. See also Davison, 1995. Thank you.
Thank you, Heather, very much. I'd like to apologize. Some people can't see the slides. One of the people who couldn't see the slides rejoined the app and now it works. So if you're having problems, leave and then rejoin, and then maybe that will work. Our final discussant for today in the pre-selected list is Christian Hennig from the University of Bologna in Italy. So Christian, over to you.
I try to share my slides. Does that work?
Yes.
Good. Do they also change?
Yes.
Wonderful. Okay, I like this paper a lot, and I will add a somewhat philosophical reflection on the question, why do we want assumption-lean methods? Probably most of us would sign up to this famous statement by George Box that all models are wrong, but some are useful. Still, there's often talk as if model assumptions have to be fulfilled and models have to be true or correct, also in this presentation. This is surely misleading. What does a model assumption actually mean? Well, it means that there is some theory that characterizes the behavior of a method assuming that model. It surely does not mean that a method cannot do well if the model assumptions are not fulfilled. Otherwise, because all models are wrong, we could never apply anything model-based. So actually, the reason for assumption-lean approaches is not that the assumptions would be more often fulfilled or they would be more often correct, right? Because as for assumption-heavy methods, they never are. Now, it is of course sensible to question the behavior of model-based methods in case the model is not true. How do we do this? Well, we set up other, maybe bigger nonparametric models relevant to the application in hand and see what the methods do. And this was actually done by the authors. Now, assumption-lean methods come with a bigger variety of methods for which this is already done in theory. This doesn't automatically mean, although of course one can check this in many special cases, that they work better overall. Okay, the present authors focused on estimands. Now these are still defined within big non-parametric models, right? If there's no true frequentist model, there's no expected value, and there's no well-defined estimates. These are not model-free. Actually, I don't claim this is a problem, right? Because models basically serve this purpose that we can think about things in this way. But if it is not, being assumption heavy isn't necessarily a problem either. Now, I was reminded of the paper which is called More Honest Foundations of Data Analysis by John W. Tukey. And there's a focus on procedures to be challenged by a variety of relevant models, none of which is assumed true. The advantage of thinking in terms of procedures is that there's a clear separation of fictional models versus the procedures that we can compute and have observable outcomes. Now, there's also an advantage of looking at estimates. Namely, we can discuss not only the information in the data, but also whether we are estimating is really what we are interested in, which of course cannot be decided by the data. I think that's actually a great feature of the paper. Of course, also of Vanessa's and some other discussion, and Tukey would have liked that. However, there are more aspects of this than are actually discussed in the paper. Now, I'm going to consider one-dimensional location estimation, and one thing that we know from standard robustness theory is that the expected value is actually not a robust functional. So, for example, if we consider distributions like this, right, large proportion of a normal distribution, a very small proportion of another one, we may be interested in estimating actually the large proportion because we may think that the other one is just kind of bunch of irregular outliers. Now, the expected value of this distribution, which is all fine according to asymptotics, is this, which is outside the large density region of the big normal. What we actually normally want to estimate is actually the mean of that. And there are similar effects in the paper, right? The estimates are all based on the expected value, which has an unbounded influence function. The influence function in the paper is also unbounded. So they are potentially critically dependent on small remote subpopulations and may in some sense not estimate exactly what we want to estimate. So assumption-lean doesn't necessarily imply a desirable behavior over the whole range of the models that is covered by the assumption-lean theory. Actually, this was already noted in Bouya's much cited 2019 paper. And these procedures may come with some hidden requirements that go beyond what's an asymptotic theory. Thank you very much.
Thank you very much, Christian. Thank you. I would now like to call on the authors to reply if they wish.
Okay, well, thank you very much for really many interesting discussion points on which we will obviously communicate in detail in the rejoinder to the paper. But I would like to take a few minutes maybe to pick out a couple of points. First of all, let me be clear again that we are clearly not attempting to sort of move away from what's viewed as the ideal in causal inference. And indeed, if I had the occasion, I would also sit around a table with my clinical collaborators to see how we can refine the population of interests and then focus on that. And probably I would view that typical causal inference approach as more ideal than what we have in the paper. But I do have a few concerns, and that is there's many analyses being done in practice, and there's very few people who can sit around a table with me. So also when I'm teaching short courses on causal inference, people come to me with questions all the time, and it seems like very often we need to spend quite a bit of time to do like a clean causal analysis. And so our attempt has really been to I think we're really hoping to sort of improve standard practice where maybe the perfect solution is not really within reach, and I think this proposal hopefully comes close to that. Maybe to add a bit support to this, it's not too hard to find causal inference papers by causal inference experts where there was not really an attempt to delineate the population of interests, and I think it's also easy to find cases where we end up using logistic models like marginal structure models where there is some adjustment for covariates in there, where it's not really clear how that choice of covariate set was really selected. So I think a lot of the issues that were mentioned, I think the causal inference approach is not entirely free from it because we have to face the limitations of the data. And so I think we're mainly aiming to hand something to people that they can hopefully use or sort of relate to, again, when the perfect solution is not within reach. A couple of people mentioned the expression of the estimand, which is indeed looking rather ugly and not the kind of thing you would want to communicate to your clinical collaborator. But as I view it, is a bit, as I try to explain it in the talk, within each stratum, there is an effect estimand, if you like, or some association measure. And at the end of the day, there's a whole distribution of them, and we try to summarize that. We've only looked at the mean or some weighted average. I think it would be much more insightful if we would also look at the weighted variance. And then if we learned that the variability was pretty tight, then I think we have learned more than with a marginal effect, because we would know that something would apply to most covariates straight up. Maybe I'll add one last point, and that is I think, like all effect measures have their limitations. Odds ratios are non-collapsible and have their limitations, but relative risks can take different magnitudes, whether you look at the relative risk of dying or being alive. I think to really get a full understanding, we need to look at baseline risks as well. And David Spiegelhalter has this very nice tool. I forgot the name, where you could sort of supplement your odds ratio with baseline risks, and probably this is also what we need to do on top of what we have done so far to sort of look at a similar analysis focusing on baseline risks, so that hopefully we can come to a complete picture of, or at least a more complete picture of treatment effects. Maybe I'll give Oliver a chance to add to my comments. Thank you.
Yeah, so I'll be brief because I know that we don't have much time left. Of course, thank you very much to all the discussants for the many interesting points. So I think that, of course, in a way, like, for example, the discussion of Peng was touching upon issues like marginal versus conditional effects that I think are ongoing in causal inference, and surely the discussion of which is more useful will go on for a long time to come. I think we've really taken an approach. We've kept this link. The reason our estimands maybe differ from the marginal estimands in this case is that we've really tried to keep close to the model parameter, because we've strived for a generic class of estimands regardless of what kind of exposure you use, and for the inference also to be generic. And I think that for these marginal contrasts, Peng gave us an example. One would have to throw away several of the criteria we used when choosing an estimand. Finally, Vanessa talked about the efficient influence function as being a miracle. So I really wanted to say that this is kind of efficient influence functions have been around a lot longer than machine learning has. Well, depending on how you define machine learning. And of course, there's, we're still making assumptions here. Just it's maybe harder. It's not like the usual assumptions of model misspecification that are harder to communicate to students. So, of course, if the machine learning approximation is very poor, that it's not that our estimators are nevertheless going to behave well. So, of course, I think there's a lot more to be done about developing better, maybe machine learning estimators that are targeted towards higher quality estimation of a parameter. And yeah, I'll leave it there and hand over to the chair again.
Thank you very much. Just stop my timer, otherwise it will blow up in a minute. And of course, the authors will have the opportunity to give a more considered reply in the journal in due course. And thank you very much for your reply there. Judith has reminded everybody in the chat that if anybody else wants to make a written comment of 400 words and have that contributed to the discussion published in the journal, please send it to her. Her email address is in the chat, j.shorten@rss.org.uk by the 20th of July. I'd like to thank very, very much both authors for spending a lot of time today telling us about their work, and also giving the demo a lot earlier as well. So thank you very much for that too. Thanks both to the proposer and the seconder, and all of the discussants who've come along today and made this such a wonderful meeting. And I'm sure we've all learned a huge amount. I certainly have. I know you will as well. So thank you very much. I'd just like to finish by saying that the next discussion meeting will be announced on the RSS website and announced in members' newsletters and on Twitter in due course. The next one will be held at the RSS annual conference on Wednesday, the 8th of September at 5:15 p.m. And this is going to be a multi-paper event on aspects of the COVID-19 pandemic. If you'd like to be informed personally about all future discussion meetings, please email journal@rss.org.uk to be added to the distribution list. So thank you very much, everybody. Nice to see you, and hopefully see you again. Bye.
Thank you. Very nice.
Thank you very much.